Hello everybody and welcome back. Professor O'Hara here, and we're going to be starting the written questions on our sort of practice midterm, but it's not quite a midterm. And one of the main reasons that I'm not actually calling this a practice midterm quite often is because there's less multiple choice questions than we're having on our midterm. There's more written questions than we're having on our midterm. But most importantly, this wasn't ever a midterm. And I haven't actually tested these questions to see whether or not altogether they'll take about 2 hours for a student. So this is not really a test. But, what can we say here? Well, they're good questions. They're in the exact same style as our upcoming midterm. I have included more written questions because there's lots of different ways that we can have written questions. Yeah, we only have, I think, 2 written questions on the upcoming midterm, maybe 3. But there's lots of different written questions you can have, and so why should I include only like 2 or 3 written questions here? You know, a limit question, a find the derivative question, and then an implicit differentiation question, when there are more things that could be asked. Okay, we're going to see an intermediate value theorem question in a little bit. Not question 28, of course. Okay, so I wanted to show you a wide variety of things. Now, these are written questions. And they even bother to state here, in the questions that follow, you are required to show your work. Questions without sufficient justification will not receive credit. So, this means a couple things. One, you actually have to talk, write out in sentences every once in a while, show your calculations, show your work. Okay? More important than that is justifying your steps by saying, okay, I went from this line to this line with the product rule. Or I went from this line to this line by factoring something out. If it's not obvious exactly what you're doing in your calculations, say what you're doing. Makes it easier for us to follow when we're marking, and a happy marker is more prone to give you more marks. But also, if you show us what you're doing, you'll earn more marks because you're doing what we asked. Okay? I think there's a question later on, I think it might be question 31 or something like that, that is just a find the derivative style question. If you were to, on scrap paper, do all your calculations and just write the answer, you're going to receive almost no marks, possibly even just no marks, because you didn't show what you were doing. You didn't say things like chain rule, or, okay, here's the definition of continuity. Okay? If you're going to use results like squeeze theorem or intermediate value theorem, sometimes it's even a good idea to state what you think the theorem is and how it's going to apply. Okay? These are the things that must be done to get full marks on a written question. Now, it's not all that bad, it's not particularly scary, and one of the reasons I'm making these video series is so that we can do some written questions together and you can see how much I'm writing to justify, so that way you know what sufficient justification really is. Alright, but enough chit-chat about what written questions actually are. Let's get into question 28, and then we'll do question 29 in the next video. I will say, just a word of warning, if you think my handwriting in class is bad, you haven't seen anything yet, because I'm going to be writing up solutions here in my own handwriting. So question 28, let f of x be... Alright, so we've got a piecewise function. When x is 2, f of x is 5. But when x isn't 2, either greater than or less than 2, we get x squared plus x minus 1 over the absolute value of x minus 2. And that's kind of interesting. I might even try and graph this. Now, they're focusing a lot on the 2's. The x minus 2 draws my attention. I might even wonder, is 2 a root of the numerator, the x squared plus x minus 6? Quick calculation in my head confirms this, and this might be important in a little bit. Okay. So what are they asking us to do? Well, we've got a few parts in this question. 5 parts to be exact. Yeah, it is 5, right? Yep, 5 parts. And the first 3 are find limits. Limit as x approaches 2 from below, 2 from above, just plain old 2. Now, if we think about it for a second, this is a 2-sided limit. Those only exist if the 2 one-sided limits exist. So really, by doing 1 and 2, we can get 3 quite quickly. 4 and 5 are both asking for continuity at different values of x. Okay, so we might need to justify some things there. Okay. We might need to remember what is continuity. It might be a good idea at some point to say the definition of continuity is this, 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 and this. Alright, but what have we got first? The limit as x approaches 2 from below. So I might start off by saying x approaches 2 from below means we only consider x values that are less than 2. So the limit as x approaches 2 from below of f of x is the limit as x approaches 2 from below. Well, the function's never actually going to be 5, so it's x squared plus x plus 6 all over the absolute value of x minus 2. Okay. So, what can we do? Well, let's see here. Okay, so x squared plus x, I might even just do this as a side calculation. X squared plus x minus 6, it's minus 6. Had a little mistake there. This 2 is a factor here. We can see this either with the quadratic formula, or we could try and factor it out in our heads. 2 and minus 3 are going to be the roots here. Okay? So that tells me that I've got the limit as x approaches 2 from below of x minus 2 over the absolute value of x minus 2 times x plus 3. Okay. What can I do from there? Well, we did an absolute value over the function style limit in class. You might remember we showed that the absolute value function y equals absolute value of x has no derivative at x equals 0. It's going to be the same sort of thing. I'm going to use product law to break these guys up. Remember, I can only do this if these limits both turn out to exist. If they don't, I've got to go back to the drawing board. But I've got a good hunch here. And we might even, in brackets, say product law. Okay. Now, the one limit, x plus 3, as x goes to 2, this is going to go to 5. And then, well, the limit as x approaches 2 from below of x minus 2 over absolute value of x minus 2. Well, if x is always less than 2, x minus 2 is always less than 0. So absolute value of x minus 2, this is a negative number, so negative numbers get made positive. Okay? So really, this is 5 times the limit of x minus 2 from below, x minus 2 over negative x minus 2. This is 5 times the limit of negative 1. Because the x minus 2's are going to cancel out, and we'll just be left with 1 over negative 1. So our answer here is a limit of negative 5. Now, you could probably write it a little neater, a little more organized than I did, but everything that needs to be there is there. All right. Now we're going from above. So x is going to approach 2 from above. So x is above 2, and now I can make the observation that means x minus 2 is greater than 0. So the absolute value of x minus 2 is just x minus 2, because it's already positive. I don't have to make it positive. Okay. So that's going to help us. Going to make this one's going to go a little faster than 1. So the limit as x approaches 2 from above of f of x is the limit as x approaches 2 from above of x squared plus x minus 6 all over absolute value of x minus 2. But in this case, that's going to be the limit as x approaches 2 from above x minus 2 times x plus 3 all over x minus 2, because I was able to simplify this absolute value of x minus 2. Now these cancel out, and we're left with the limit of x plus 3 which is 5. See how much faster that one went? Okay. All right, so we've got a limit of -5, and I might even put a box around that so it's really clear to whoever's marking. These are my numerical answers. Now we're being asked in part 3, find the limit as x approaches 2. So I might say something like two-sided limits exist only if the one-sided limits agree. Okay, so they exist only if the one-sided limits agree. That's fine. Well, the limit as x approaches 2 from below of f of x, we saw that that's -5. But that's not 5, which is the limit as x approaches 2 from above. So the limit here does not exist. And that's exactly what I would put. All right. Is f of x continuous at x equals 2? Why? Well, the answer is no, it's not continuous. We might say something like, to be continuous at x equals 2, we need f of 2 and the limit as x approaches 2 of f of x to exist and to be equal. But by question 3, part 3 here, the limit as x approaches 2 of f of x does not exist. So f is not continuous at x equals 2. Okay. Now for 5, is f continuous at 0? All right, so there's a couple things we could do here. A couple things spring to mind. The first thing that springs to mind is, well, we could just do all these calculations again, but instead of doing the limit as x approaches 2 from below, we do from 0, approaching 0 from below, or 0 from above, and show whether or not the two-sided limit exists, and then asks, does f of 0 exist, and are those values equal? That's fine. I suspect that's why they give us a whole lot of room on this page. Either that or they just couldn't think of another question to ask. Okay, another limit-style question to include in 28. And that's fine. The other way I could see to do this question, remember, and you may have to dig back in your notes, that we can make new continuous functions from old continuous functions. Okay? And remember that we discussed, well, if f is continuous at a and g is continuous at a, then f plus g is continuous at a, or f minus g is continuous at a, or f times g is continuous at a. So we might remember things like that. And if that's the case, well, we can do this question in a different way. Okay? So, well, we've got some space. I think I'll do sort of the fancy way, the last one that I just, the using results way. I'll do that. Then I'm going to erase it, and I will finish this question off by doing it the longer limit-based way, because that's the way I think most people will do it. But there's a slightly faster way. So I might say something like, near x equals 0, f of x and x squared plus x minus 6 over the absolute value of x minus 2 are identical. Okay? It's only when we get out near 2 that these functions might switch around a little bit. Okay? Now, so f is continuous at x equals 0 exactly if x squared plus x minus 6 over the absolute value of x minus 2 is. Okay? Now, x squared plus x minus 6 is a polynomial. Therefore, it's continuous. And the absolute value of x minus 2 is continuous. And, really importantly, absolute value of x minus 2 is not 0 at x equals 0. In fact, it is 2. Okay? And this is really important because you might remember from class, a quotient of continuous functions is continuous at, say, x equals 0 if the bottom function is not equal to 0 at x equals 0. We did learn this result. You're going to have to check your notes, but it really is there. So that tells me that x squared plus x minus 6 over the absolute value of x minus 2 is continuous at x equals 0. This function isn't continuous. We've seen it's not continuous at 2, but it's actually continuous everywhere else. Therefore, f is continuous at x equals 0. Okay? So that's sort of the fancy way to do this. We're not doing a whole lot of calculations. It's more just sort of results and theory. Okay? F of x looks exactly like this other function, near 0. Continuity is a very local property. So f of x is continuous only if this other function is. Well, this other function is a quotient of a polynomial, always continuous, and a function that is continuous at 0 and isn't equal to 0 at 0. So our theory from class fills in the rest. Okay, so that's one way to do it. You get full marks by doing something like that. Okay, now just stand back, pause the video if you want to copy that down, or rewind, because we're going to do it the way that I think most people will probably do it. It's certainly the way that will be most fresh in your mind, because it's the exact way that we were trying to do the continuity stuff in parts 1 through 4. Find the two one-sided limits, put them together, and that's a fine way to do this question as well. So the limit of f of x from below, the limit of f of as x goes to 0 from below, of x squared plus x minus 6 over the absolute value here, we can actually plug in. Now, should we plug in? Well, not really, because that's sort of assuming this is already continuous. But you can just plug in. I wouldn't. I'd be worried about losing a half mark or something. But we can do exactly the same work we did before. So x minus 2, x plus 3 here. All over absolute value of x minus 2. Now, for values of x below 0, x minus 2 is always below 0, because x is already below 0, and we subtract things from it. So x minus 2 is below 0, it's negative, so absolute value makes negative things positive. How does it do it? By multiplying your negative thing by a negative 1. A negative 1 times a negative thing becomes positive. Every year somebody comes and says, well, this can't possibly be positive. You put a negative sign in front of it. But negative of something that's already negative becomes positive. Okay? So we get the limit as x approaches 0, x minus 2, x plus 3, or x minus 2. Get some cancellation going. And we get a value of 3. Now, for x greater than 0, this is where it's a little tricky, because you can't say, well, if x is greater than 0, x minus 2 is one thing or another. But you might say eventually the values of x that we consider are less than 2. Okay? This is true. The x values that we consider when we do a limit, they get closer and closer to 0. So eventually we're going to stop dealing with things like x being 4, x being 3. Those are very far away from the actual value of x equals 0 that we want to consider. And what's happening? Well, the x values are getting closer to 0. So eventually they'll get close enough that I can guarantee that they're less than 2. Okay, think about that. If I can guarantee they're less than 2, then x minus 2 will be less than 0. Because x is less than 2, subtract 2 from both sides. So once again, the absolute value of x minus 2 will be negative x minus 2. And we can simplify this. X minus 2, x plus 3 over negative of x minus 2. Oh, I forgot to do a negative sign back here. So it'll be negative 3. Oh, these should be pluses. Negative of x plus 3, and this is going to be an answer of negative 3. Okay, need a bit more space. All right, but the limit as x approaches 0 from below was negative 3, and that's the same value as x approaches 0 from above. So that tells me the limit, just as x approaches 0, the two-sided limit, exists and equals negative 3. Okay, that's important information. Now I just need to ask, okay, what's f of, not negative 3, f of 0? Okay, just as a little aside, the most common error on quiz number 2 was that people, all classes and all different quiz sections, A, B, or C, everybody had a piecewise function. You had to show whether or not it was, you had to find values of A and B to make it continuous. The number one error, the number one way people lost marks on that question was to not talk about f at, I think all of them were at 4, so f at the actual value. Everyone did limits. A lot of people did some great limits. Okay, a lot of people used a two-sided limit when you shouldn't, and you got dinged for marks on that. But so many people never said f at 4 is this, and you lost marks, because continuity is about limits, yes, but it's also about the value of your function f at the specific point. That has to match the limits. If you don't ever talk about f at that point, you're not really going to be considering continuity. So, what is f at 0? Well, 0 isn't 2, so this should be 0 squared plus 0 minus 6 over the absolute value of 0 minus 2. This is minus 6 over the absolute value of minus 2. This is minus 6 over 2. This is minus 3. F at 0 and the limit as x approaches 0 of f of x both exist, and they agree. So f is continuous at x equals 0. That's another way to do the problem, and it's probably the way most people would try to do this. Get both of the one-sided limits, show the two-sided limit exists and is minus 3, show that f at 0 exists and is minus 3. Since they agree, that satisfies the definition of continuity, which we already stated in part 4, but if you wanted to be extra cautious, state it again in part 5. Okay? The only thing that I think is tricky for people about this one, the presence of the absolute value usually messes a lot of people up when we do limits, but I think most especially is this part right here. We're used to, even when we do absolute values, just like we did in the other 3 times we calculated one-sided limits in this question, we're used to saying, well, the x's we're considering are always greater than 2, or they're always less than 3. And so that tells me what about the absolute value? Very rarely do we have to stop and say, yes, the x's we're considering are positive, but at some point they'll also be within a certain distance. This comes up when we do some absolute value questions, and it's something you really need to stop and think about. Okay? What really is the nature of limits? Limits are, what is the behavior as you get close to 0? Okay? And when you think about that and making that calculation, if you're trying to get close to 0, does anyone really care what happens out at 3 or at 2? No, they're far away. Yeah, maybe something weird happens at 2, or maybe the function goes to infinity at 3. But those guys are kind of far away from 0. And you might say, okay. But what about if we're at 1? That's kind of close to 0, or a half, or 0.25. Yeah, but as we consider values that are getting close to 0, eventually we're going to be considering numbers smaller than a half, or a quarter, or an eighth. So if our limit is going to 0, eventually our numbers can be made close enough to 0 to make any calculations simpler and nicer. And that's exactly what we did here. Okay? If I had just come along and said, well, we're doing the 0 plus, 0 from the greater side, and we come along and we say, okay, x is greater than 0, so what's x minus 2? Well, all I can say is it's greater than negative 2. Well, that doesn't help me simplify absolute value of x minus 2, because some of these are going to be close to minus 2, and therefore negative. But some of these values are going to still be positive, and that doesn't really help me simplify things. It doesn't help me calculate the limit. So we have to go a little step further and say, eventually, things are going to be less than 2. And that means that eventually the x minus 2 values will be negative. Okay, as we get closer to 0, the x minus 2 values become negative, and so absolute value of x minus 2 becomes negative of x minus 2. All right? It's a hard concept, and if you're having trouble with it, by all means, go to the help centers. Okay, the TAs there are, in theory, trained to help you. Or if you want to, email me and say, look, I'm still struggling with this concept. Could we meet sometime after class or something? When are you free? And I'll see what I can do. Okay? So that's question 28. We still have some more written questions to go. Up next will be question 29. I will see you for that in the next video.